This is linear algebra, in college summer school class. And this is the first lecture. So my name is Nathanson, and let me just start off with some information about the class. First of all, summer school is very intense. Semester is 4 weeks long. The ordinary semester is 4 months long, so that means in every week we cover a month's work, and every day, 4 days a week, we cover a week's work. So you really need to stay on top of the material, not fall behind, do your homeworks, turn your homeworks in on time. Everything is done on Zoom, and these lectures are on YouTube. All communication is back and forth by means of Blackboard. Blackboard has an email address for you, and that's how I send you emails. You submit your homeworks on Blackboard. You submit your exams on Blackboard. So as quickly as possible, you need to become familiar with the Blackboard website for this class, especially if this is the first time you're using Blackboard. We are not having there's no textbook that you have to buy. Instead, I'm preparing lecture notes. Let me just show you the first chapter, which is already posted. So this is chapter 1 on linear equations and vector spaces. It's on Blackboard, and I think I also emailed it to everyone. So you need to follow the text. If you want supplementary text, there are a huge number of linear algebra books, all of which are decent, and you can supplement your lecture notes by looking at any book you might want to, but it's certainly not necessary. So let's get back to work, and I'm going to start with chapter 1, section 1. Chapter 1 is linear equations and vector spaces. I also posted as a kind of an appendix a set of notes having to do with sets, functions, and so forth. And that is only for reference. If in the text there's, for example, some set theory you're not familiar with, then you can just find out about it written up carefully in the appendix. But all the homeworks will come, there won't be any homework from the appendix. The homework, the first homework set, for example, comes from chapter 1 on linear equations. So let's get started. So this is the way we teach this course. So chapter 1. Section 1.1, chapter 1, section 1. One linear equation. This is the starting point. This is linear algebra. It begins with linear equations. 2x equals 3 is one linear equation in one variable, and the solution is x equals 3/2. You would have an equation like 4x plus 7y equals 5. This is one equation in two variables, which I wrote here as x and y. Or 3x minus 2y minus 5z equals 17 is an equation in three variables, x, y, and z. There's nothing special about the variables. I could write 3x1 minus 2x2 minus 5 x3 equals 17. And here, my three variables are x1, x2, x3. You can use any letters you like for variables. X, Y, Z, U, V, W makes no difference whatsoever. And there is a rough classification of linear equations into homogeneous and inhomogeneous. An equation like 4x plus 7y equals 0 is called homogeneous. that means that the right-hand side is 0. An equation like 4x plus 7y equals 5 is inhomogeneous or not homogeneous because the right-hand side is not 0. The general linear equation can have any number of variables. And a standard form to write the linear equation is a1x1 plus a2x2 plus a3x3 plus ... plus a sub n x sub n equals b. So this is the standard linear equation in n variables. And if b is 0, it is homogeneous. And if b is not 0, it's inhomogeneous. Also recall, like you learned this in calculus, if you have numbers or quantities, they can be added. U1 plus U2 plus U3 plus U4 can be written using what's called sigma notation. You take the capital Greek letter sigma, the I goes from 1 to 4, U sub I, it means this. Or, so for example, summation I goes from 1 to 8, I means as I goes from 1 to 8, I goes 1 plus 2 plus 3 up to 8. Which if you add it up is 36. Or if you add, it doesn't matter what letter you use for summation. If you have summation j goes from 3 to 7, j squared, this means 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared. If you add it up, I believe it comes to 135. So this is what is called sigma notation. Again, it's used in calculus, so you've certainly seen this. And the general linear equation, you could write a summation. I goes, or let me write this, j goes from 1 to n, a sub j, x sub j equals b. So this is just notation, which we use all the time in linear algebra. Suppose we have an equation like 4x plus 7y equals 0. So one solution is x equals 7, y equals minus 4. Because 4 times 7 plus 7 times minus 4 is 28 minus 28 is 0. Another solution is x equals 6 and y equals 3/7, because 4 times 6 plus 7 times 3/7 is 24. Oops, I should make this 4/7. Is 24. Oops. Sorry, the wrong equation. X equals 6, y equals minus 24 over 7. Because 4 times 6 plus y times minus 24 over 7 is 24 minus 24 is 0. In general, we write a solution of the equation a1x1 up to an xn equals b as a vector, an n-dimensional column vector, x1, x2 down to x sub n. So for example, if I take x equals 7, y equal minus 4 for this equation, the vector 7 minus 4 is a solution of 4x plus 7y equals 0. The vector 6 minus 24 over 7 is a solution of the same equation. There are lots of solutions. In general, we write solutions of equations in vector form, column vectors. And the set of all n-dimensional column vectors with the xi's, these numbers that occur in the vector, are called the coordinates of the vector, with real number coordinates is Rn, R superscript n. So this means the vector space, we call it a vector space, I'll define it shortly. This is the set of all n-dimensional column vectors. In linear algebra, we use real numbers and complex numbers. So you could have, in the complex numbers, you might have the equation I times x plus 2y equals 0. And one solution might be I, 2i, 1 is a solution, because I times 2i plus 2 times 1 is minus plus 2 is 0. And by Cn, this is a set of all n-dimensional column vectors with complex coordinates. So one thing one has to learn, become familiar with in the class, are the complex numbers. In most of the examples, I'll be using real numbers, but every theorem in this chapter, and for almost all the chapters in this course, everything applies equally well to real numbers and to complex numbers. And I will add a second appendix just dealing with complex numbers if you're not familiar with them yet. Suppose we take the inhomogeneous equation, 4x plus 7y equals 5. So for this inhomogeneous equation, three minus 1 in R2 is a solution. It's in R2 because the coordinates are real and the dimension is 2. The number of coordinates is 2. Why is this a solution? 4 times 3 plus 7 times minus 1 is 12 minus 7 is 5. So that's the solution. If you have a linear equation in n variables, this is called the zero equation. If all of the a's are zero, that's always kind of a weird special case. And the equation is non-zero if ai is not zero for at least one I. At least one A sub I. And often we'll say we really just dealing with non-zero equations. If you have the zero equation, if all the A's are zero, if B is zero, every vector is a solution. And if B is not zero, no vector is a solution. So we've completely described the solutions of zero equations. Equations in one variable have one solution, which is unique. I should always emphasize non-zero equations. So your non-zero equation, a1x1 equals b, has a solution. x1 is b over a1. a1 is not zero because the equation is not zero. You can divide by it. And equations in two or more variables always have infinitely many solutions. And what is called the solution space of an equation is the set of all solutions of the equation. So for example, suppose we have the equation 4x plus 7y equals 5. We want to compute the solution space. So you could say, well, 4x plus 7y is 5. 7y is 5 minus 4x. So y is 5/7 minus 4/7 x. So your solution xy has to be x, and then the y is equal to 5/7 minus 4x over 7 for all x. And the way we would write that is the solution space is the set of all vectors x for the first coordinate, 5/7 minus 4/7 x for all x in R. So this is mathematical notation. This is the solution space. Now, there are other ways to write the solution space, but any one way, there's only one solution space, even though it might have different descriptions. Let's look at an equation in 3 variables. So we have 3x minus 2y minus 5x equals 0, minus 5z equals 0. So one solution is the vector 1 minus 1, 1. because 3 times 1 minus 2 times minus 1 minus 5 times 1 is 3 plus 2 minus 5 is 0. But we want to find all solutions. So you could say, well, let's solve for z. So 5z is 3x minus 2y. So z is 3/5 x minus 2/5 y for any x and y. So the solution space is the set of all vectors x, y, and the third coordinate is 3/5 x minus 2/5 y for all x and y real numbers. That's the solution space. Let's look at an inhomogeneous equation. Suppose we have 3x minus 2y minus 5z equals 17. So if we solve again for z, we would get 5z equals minus 17. Plus 3x minus 2y. Or z equals minus 17/5 plus 3/5 x minus 2/5 y. So my solution space is the set of all vectors x, y, minus 17 over 5 plus 3 over 5x minus 2 over 5y for any values of x and y. So for example, let me just double check and make sure this is correct. Looks okay. Suppose I let x and y be 1. If x and y are 1, z is minus 17 over 5 plus 3 over 5 minus 2 over 5. What is that? That is minus 14 minus 16 over 5. Let's check. 3 times 1 minus 2 times 1 minus 5 times minus 16 over 5 is equal to 3 minus 2 plus 16 is 19 minus 2 is 17. It checks. And no matter what values I pick for x and y, if I use them to calculate z, I will get a solution of this equation. That's pretty good. So this is section 1.1, and there's some homework for Wednesday from this section. That's all for this.